Okay. And for the last talk of this little breakout session, we'll have Shilin Lai talking about Frobenius fields of abelian varieties.
Okay, thank you for the opportunity to speak. This is joint work with my postdoc mentor, Akshay Brunugale, and his former PhD advisor, Haruzo Hida. So it took 3 generations of people to write this. It's only 20 pages, the paper, so it's really short. Okay, so the basic question is about the Frobenius field of abelian varieties. Let's start with an abelian variety defined over a number field K, where of dimension G. The Frobenius field of the abelian variety FAV is the field over Q generated by the 2G Frobenius eigenvalues of A at the place V. So this in general is going to be it's going to be a field generated by 2G elements, so it has diminished degree of at most 2G factorial. It's Galois and CM in general. Okay, so we are interested in this field. And the behavior of this field fundamentally depends on whether or not the abelian variety has CM. If abelian variety has CM, complex multiplication, then the CM theory of Taniyama-Shimura tells us that the Frobenius field is going to be contained in a subfield of the CM field. And if you do some Chebotarev counting argument, you can even say that for density 1 set of places, it is equal to a specific subfield that you can write down based on the CM data. In contrast, there doesn't seem to be any relation between those fields when A doesn't have CM. So if you take a typical elliptic curve, look at the Heike polynomial x squared minus APX plus P equals to 0, the field defined by this polynomial seems completely random based on P. And that's more or less the Land-Torter conjecture. So our main result is a small piece of it. Our main result says, oh, okay, first, even before that, there should be a result that there should be an assumption that A does not have potential CM. So A does not have CM over an algebraic closure. And then there's a technical assumption that the monodromy group of A is connected. We hope we can remove that eventually when we can be bothered. Maybe a 4th generation will show up. Anyway, so that's purely technical. Then we can show that the Frobenius number field is equal to a given number field for density 0 set of primes. So it's, yep. And we think that our method of proof applies to any compatible system of Galois representations. If it's semi-simple, and it also should say coming from geometry, but also if you believe Langlands, Fontaine-Major, all of them come from geometry. So, you know. Yeah, I wrote the slides yesterday, so there are many typos. Okay, and the screen hates me. I know. What's not really the solution?
So it's not.
I'm
Projector's reset.
moving my mouse around.
Yeah, the computer's fine. The projector.
Okay, very good. I mean, it should hit me on the next slide, which is we have a quantitative version. Same assumption, again, I forgot to include the suppose A does not have potential CM. So if A does not have potential CM, again, technical assumption, monodromy group of A is connected. We introduce this like GB is a Moffett-Tate group of A. It doesn't really matter what it is, it's some group that's attached to A. It's G derived, is a derived subgroup, doesn't really matter. If for elliptic curves, it's GL2. So for this group, I can count the number of places less than or equal to X, count by norm, such that the Frobenius field is congruent to equal to M. And it's this number. You know, it's a number. 1 is the obvious bound, 1 minus is a small number. not really important. For elliptic curves, we got x to the 13 over 14 plus epsilon. Conjecture is x to the 1/2. And I think the current record is the one by Kojikaru David with x to the 4/5. Yeah, we didn't really try very hard with exponents. So this big O notation, so of course it depends on A and epsilon, but an annoying thing is it also depends on M. So for different M, I could have a different constant. This is vaguely irritating. So we can get rid of it, but I get a way worse exponent, which is 4 times the dimension instead of 3. I don't know what we should expect here. I don't know if the 1/2 Elan shorter is 2 because the elliptic curve or 2 because square root cancellation. So I have nothing intelligent to say. I don't even do analytic number theory. Anyway, that's our second main result. So first is cut off, but the section title is proof in an ideal case. I'm going to show you a proof where literally everything is as nice as possible. So for that, we introduce the Galois representation, which we saw on the last talk, where G is equal to 1. So this GSP2 is just equal to GL2. So we have a Galois representation sending Gal K into GSP2 GZP, and then we can take the product over many primes. So we have an idyllic Galois representation. And our assumption is what's known as the abelian variety is generic. So it has a idyllic open image in as large of a group as possible. So it has open image into GSP2G, say, idyllic points. So in this case, there is a paper in 2018 by Samuel Bloom proving our results, but our exponent is slightly better. He had this exponent, we improved it to this exponent with this additional dependency. And I claim the method is different, but it might not be if you look hard enough. I don't know, maybe. Anyway, here's our method. So our method is considering conjugacy classes of Frobenius torus. So here is where here is where the dependency M comes in. I'm looking at a prime where M splits completely. So that's a positive density set of primes. Suppose FAB is equal to M, then I'm going to use that to eventually derive some Chebotarev condition on V. So if FAB is equal to M, then all Frobenius eigenvalues of A lie in ZP because M splits completely in at P. So this plus 14 semi-simplicity tells you that the image of Frobenius lies in a split torus. But when you reduce from ZP to FP, semi-simple elements can be sent to unipotent elements because 1 plus P, 1 minus P both reduce to 1. Even though semi-simple is no longer semi-simple necessarily, it still lies in a Borel subgroup. And I can count Borel subgroups. So the union of all Borel subgroups is not all of GSP2G FP. It's something strictly less than 1, plus something that's big of P inverse. And now the Chebotarev argument goes through as usual. We have this, if you take R to be a finite set of primes where M splits completely, then I get, by our simplifying assumption of idyllic openness, we know that this map is surjective. And for each P, it lands this BP, which I use to denote the set of all Borel elements, which lie in a Borel. And the previous local calculation tells you this less than is bounded away from 1. I don't know a better notation. And so by Chebotarev, each of the terms is bounded away from 1. The product can get as small as possible. Chebotarev tells you the density is 0. That's the qualitative statement. To do the quantitative statement, my first idea was to use Lagarius or Liskow's effective Chebotarev. Not good enough, just barely is off by a log. So following our idea of Serre, we are using the Selberg seed. Sayre actually proved everything I had said for elliptic curves in his paper, Some Applications of Chebotarev, except he just stated the result and says this can be proven, as Sayre does. So following Sayre's idea, we use the Selberg sieve to get the power saving. And the actual place where improvements comes in between 3 dimensions of G and 4 dimensions of G comes in these observations as a broad subgroup of GSP to GFP is what's known as a super solvable group. If you don't know what a super solvable group, it means it implies all of its irreducible characters are induced from one-dimensional characters. And the usual L function nonsense tells you that Artin holomorphic conjecture is known. So we can use the improvement found by Murty Sarada for the effective Chebotarev error term. So this gives us a quantitative statement under the simplifying assumption. And we can vaguely hope something like this is true in general. This depends on so many conjectures, in particular Moffat-Tate conjecture, which we know nothing about. So this is very hard and also vague because I didn't say anything about integral structure on G. But what we can do is we can replace it by something we do know. First, at each prime P, we allow G to be different. We replace G by the monodromy group. So Hui-Larsen proved earlier result, Winterberg J, tells you that the Galois image at each local prime is in GP that P contains a large subgroup, a very specific large subgroup. I just don't want to say the definition. And another result of Sayre says up to a finite extension, the images are independent of each other. So combining those ingredients together, we still have the result before that the image of the Frobenius lies in this product of union Borel subsets. This estimate still holds in general. The issue is the image is not going to be the full adelic image, but it's going to contain a large enough subgroup. Now, the key refinement of the original bound is that this bound is uniformly distributed in the cosets of IP. How long do I have? Okay. I'm going way too fast. That's not the point. That's okay. Okay, so before that, I just took the union of all Borels and then say this is bounded away from 1. Now I have this big open subgroup, not open, a big subgroup, and I want to say within each coset, the density of this BP is still bounded away from 1. And this combined with this kind of image result tells you the qualitative version. So you can conclude the same way as before. Okay. Any questions about the qualitative version so far? This took a page in our paper. Quantitative version took the rest of the 10 pages. So the first issue was we used the Selberg sieve in the beginning, in the last time. Selberg sieve is a very delicate object, and it requires all of the weight coefficients to be exactly multiplicative. You cannot have a single error term because it depends on very precise cancellation. But because we don't have full independence, we just have potential independence, our weights are not going to be multiplicative. So what we end up having to do is working each coset of this big group and introduce a whole bunch of notations. So that's messy. The error term in the Chebotarev density theorem also causes an issue because we are no longer assuming all of those GPs to be G. We are not assuming the monodromy groups are interpolated by Moffat-Tate group. We are allowing a different group at each prime. So those error terms, I mean, if you count the number of IP points of algebraic variety, you know it's P to the dimension plus an error term. But the point is I need to control the constant here uniformly in P and uniformly in GP. The way we do that is first, the Lin tells us that the connected component of GP is always contained in the Moffat-Tate group. So we have an upper bound on the dimension of the monodromy group. Okay, so now instead of considering GP, I take the semi-simple, well, technically you first take the semi-simple portion of it, and then you take the simply connected cover, and then change it to FP bar. Once you do that, you have a reductive group over an algebraically closed field, which is simply connected. There's a classification for those, and all of them come from base change of Shiba Lie groups over Z. Once you know that, you can uniformly control this constant. So this is base change to FP bar, but we want to count points over FP. So what you do is use Grothendieck Lefschetz trace formula. Because all of them come from base change to something from something over Z, you have you know their total homology. There's a finite list of them. So Grothendieck Lefschetz trace formula gives you uniform control on this constant. And finally, there's this cute fact I never knew about. The number of points in a simply connected cover is equal to the number of points of the original group. This is true for any S-orogeny, as it turns out. But we found this as we were working through this whole detail. Okay, so with all of those ingredients, we can go through the proof of the quantitative version of the, we can go through the quantitative proof again, apply Selberg sieve and all that, and then that's where we got our exponent, where you optimize the marginal barrier terms and all that. Okay, Abelian here.
Do you have any questions for Shilin?
Yes. Okay, so basically effective Chapel tariff density theorem, you always want to move the line, move it as far to the left as possible, and it's possible. There is an improvement if you know that it's holomorphic within the critical strip. So that's where holomorphic conjecture is used. It's going to be used. I didn't want to specify it, so it's going to be used in like the field a priori. You are looking at the field cut out by this surjection. So it's this product of GSP to GFP representations. But one thing that Murty Sarada did in their work is they noticed by some basic L function formalism, you can replace it by taking an extension of this, which corresponds to the subfield corresponding to the product of the Borel. And Artin holomorphic conjecture is known for any group whose Galois group is a product of Borel, because Borel subgroup, split reductive group over FP are supersolvable. You just prove it directly by using the usual root system argument. So in fact, what that comes down to is this assuming the GRH, we only need to assume GRH for HKL functions, which may be easier. I don't know, probably not.
Any other questions? Okay, I'm going to thank the speaker again.